Hello, in this lecture I will introduce the conformal boundary. The conformal boundary is necessary to understand the conformal compactification of solutions of the Einstein equations, which we will discuss later. Okay, let us start with a space-time, which, as we know, is represented by a Lorentzian manifold. And then let us put forward the idea of the conformal boundary. Well, what is the idea? Well, the idea is that we want to look at our space-time from the outside in order to gain understanding of properties of the space-time which we cannot see if we are inside. Well, the situation is similar as the situation which happens when you are inside a forest. If you are inside a forest, you cannot see the forest because you have all trees around you. You have to get out from the forest and look at the forest from the outside. And by doing that, you will be able to see things, such as the shape of the forest or its extension. So we want to do something similar here. But, well, the obvious question is, what is the outside of our Lorentzian manifold? We need to define that some way. And what we are going to do is we are going to introduce a larger manifold and embed our manifold into the larger manifold. Okay, so suppose that you have, this is going to represent our space-time, okay? And then we are going to choose a bigger manifold, a bigger Lorentzian manifold, so this is going to be a bigger space-time, and we want just take our space-time and put it inside our the bigger Lorentzian manifold. By doing that, we will take the bigger space-time as the outside, and so we will be able, by putting ourselves in the bigger manifold until that we will be able to look at our space-time from the from the outside. And so we will be able to define things such as the shape of our space-time or the boundary of our space-time. Okay? So how are we going to do that? How are we going to embed our original space-time into a bigger manifold? This is going to be achieved by means of a conformal embedding. So we are going to introduce a map which goes from M to our bigger manifold M tilde, such as that, well, phi is an embedding. Okay. So it means that, well, the image of M under phi is a proper subset of M tilde, okay? And then the map, well, the restricted map, what is the notation? What notation should I follow? Maybe, well, let me just use the notation phi bar. This map is a diffeomorphism. Okay, so this is just an embedding. So with this, what we have is that the this set here corresponds to the image phi m under the embedding. And okay, but the thing is that since this is since we are working with Lorentzian manifolds, we know that Lorentzian manifolds have something attached to them which is called the causal structure, which is defined by the fact that this G mu nu, that we have a Lorentzian metric. Okay, so we are interested in an embedding such that this causal structure is preserved in some way. And how do we get that? Well, we get that if we consider, if we demand in addition that this map is a conformal map. So what does it mean? It means that the following property is satisfied. We take the pullback of the metric of the big Lorentzian manifold, then we have that this pullback, which is now a tensor in the starting manifold, is conformal to our original metric. Okay, so this means that okay, and well, since we are assuming that our map phi is a smooth map, then it means that this function chi is also smooth. Okay. Well, that's the situation now, and well, this set, this set, the boundary of this image. Well, let me just write it down. We have the following set now. This is a subset of the big manifold, and this is the so-called. Let me just, because this is important, let me just use the red color. This is the so-called conformal boundary. Well, conformal is because we are using a conformal embedding, and the boundary is, well, because, well, this set is an accumulation point of well, sorry, it's because this is the boundary of the image of our original manifold M. Okay, but well, we must bear in mind when we look at this definition to the fact, well, we must bear in mind the fact that this definition depends on the conformal embedding we are using, phi, and also of course depends on the bigger manifold itself, M tilde. Okay, so this is not an intrinsic set which we can attach to well, it's not an intrinsic set which we can define only from the properties of M. We need to somehow invent the big manifold M tilde and the conformal embedding phi. Okay, right. And what is the point of this? What is the relevance of this? Well, this fulfills what I said at the beginning, which is that we were intending to look at our manifold from the outside, and now we have an outside, which is the manifold M tilde, and we also have a boundary at the conformal boundary, which is delta M. So it means that we are able to define we are able to define a shape of our manifold, and we will be able to define to extract properties of M, which we cannot do if we don't perform this extension, this conformal extension, because this is this conformal embedding can be also called conformal extension. Well, this will become clear when we look at the explicit examples of all of these. The explicit examples are going to be conformal compactification of certain solutions of the Einstein equations. But just before doing that, let me just mention some the relevance of this function chi, because this function chi is a function on the original manifold M, okay. But the thing is that we can also regard it as a function on the big manifold, and we can do that by just defining this other function, which is the composition of chi with the inverse map. Well, this inverse map is the map which you get by inverting this this set. Okay, so since I said that this restricted map is a diffeomorphism, then maybe I should perhaps write here the bar, because this is what we are actually inverting. So if we take this inverse, maybe I can where can I write this? Yeah, okay, I can just write this here. Okay, M. So then since we have this and we have that chi is itself a map which goes from M to R, because it's a scalar function, then of course we can perform the composition of these two maps and get this this map, which is now a scalar function. Sorry. Okay, so if we perform the composition, then we end up in a new map, chi tilde, which is a map which goes from and tilde to R. Okay, and so this the point of introducing this function chi tilde is because we will be able to use it to compute explicitly the set delta M, the conformal boundary, which is now defined as the set of points in M tilde such that they are the action of chi gives 0. So the conformal boundary is just the 0 set of this function chi tilde. Okay, and we can compute explicitly chi tilde once we know once we have an expression for the conformal embedding, right? Okay, so the main ideas are that we have introduced the conformal embedding, and with the conformal embedding we can define something which is called the conformal boundary, and I will show you later how can you use the conformal boundary to extract useful information about the global structure of our original manifold M. Okay, and this will be achieved when we compute the conformal compactification of explicit solutions of the Einstein equations, right? Okay, and this will happen in the next lecture.